What we see here are a series of curves that are all based upon a simple parabola. This is the parabolic section right here. These other curves are variations of that same parabola, so the same effective focal length, if you will, the same aperture size. They'll all be used with the same light source, in this case an LED. But what we've done is changed how we created the basic shape of the illuminator. In some cases, we were using sections along the curve, possibly a spline curve. In other cases, what we've done is swept a curve or a section curve along some polygonal output face. What we'll do now is take a look at the performance of each of these sections. The first device we're going to look at is based on a simple parabola. In this case, we have our parabolic reflector, and we've inserted an LED from the Apex light source library, and we've positioned the LED so that the dye is approximately at the focus of our reflector. And we can zoom in and see the outline of the LED within the reflector. So let's move back out. And what we can see is as the rays leave the LED and hit the reflector, they come out reasonably collimated due to the size of the LED dye. We also have rays that leave the LED and miss the reflector and therefore diverge out. Now let's take a look at the results of some analysis. And the first thing I want to look at is an irradiance plot. So what is the energy distribution on that detector surface? And what we see is a zone where we have a large concentration of energy, indicated by these two peaks here. But across the rest of the surface, what we see is effectively an almost uniform distribution of energy. This energy represents the light that is leaving the LED that's not hitting the reflector. The light that's hitting the reflector is coming out into this zone here. And the reason we don't see anything in the center here except the rays that are coming directly from the LED is that no light can hit the base part of this reflector way down here towards the center part because the LED is blocking it. And there's also the hole in the reflector. So that prevents us getting any energy in the center of our illumination pattern. This is the primary problem with parabolic reflectors. However, there is one other consideration that we want when we're using these types of reflectors, and that's to basically have this collimated light, so have the light coming out fundamentally at a very narrow range of angles. And if we look at that information for this reflector, we see that it is indeed the case. Most of the rays are coming out at a very, very narrow angular range, except those rays that miss the reflector, which are simply out here in the noise in this design. So the basic performance of the parabola is good. It's just its physical shape prevents us from getting a good distribution of energy at our surface of interest. This is why we then proceed to make other changes in the shape of the geometry. In this case, what we've done is taken the parabolic curve, but instead of using a curved section, we've effectively faceted it. So we've drawn linear segments that connect to the parabolic curve at several points along the surface. And then we've revolved that shape. And here's what this surface looks like. And now what we'll do is take a look at what the distribution of energy is. And here is the distribution across the surface. And you'll notice in this case that instead we actually get a higher concentration of energy at the center and a rather uniform distribution out over a wide range of our area. This is the result of having all those sharp cutoff angles, and as the light is incident in the areas near those angles, it's going to be redirected. In this case, it's redirected in a fashion that gives us a much better distribution of energy. Still not totally uniform, but we've gotten rid of that dead pattern in the center zone, which is actually the most important area. Now, of course, we need to make sure we haven't significantly affected our collimation. If we look at the angular distribution, we see indeed that the energy distribution is all coming out at a very narrow range of angles, which means we could use this same light source over a long distance without significantly reducing the energy distribution. For this design, what we've done is maintain the basic parabolic shape to the curve, but instead of sweeping it across a circle, we've defined a polygonal output face, and we're simply sweeping the curve relative to that polygonal section. So we're sectioning our curve based on the number of facets in the polygon. Now again, let's take a look at how that affects the energy distribution. First off, we're going to look at what the energy surface distribution is, and you'll see that there are some difficulties with this. Again, we're back to having the area towards the center having very, very little light, but we have a broader range of area that has a reasonably uniform light distribution. However, we also see the effects of each of those facet edges, because again, it's going to affect what angle the rays are coming out at, or the energy is coming out at, around those edges. So it has certain advantages over the parabola in terms of the width of the energy distribution, but it has the same fundamental problem with getting no light towards the center. And how did it affect the distribution in angular space? You'll also notice we have a wider range of angular spread on the light. So if we were to move our detector or try to illuminate at a farther distance, we would see that the light would start to drop off quite noticeably. And we also see some information relative to how the angles at each facet edge affects the light. And if we were to count these, it would be an easy way to see how many edges I had put on my polygon. In this design, we've broken our parabolic section into linear segments, and then we've also swept those based on the polygonal output face. So what we can see is these flat edges here, and we have flat edges here as well. So let's take a look at the results of the ray trace. Here we can see the distribution on our illumination surface, but now let's take a look at what the actual energy distribution is. And we can see that again, we're getting much better distribution of energy. We still have a little bit of reduction in energy towards the center, a much, much wider area of relatively uniform light, and we see a very significant spreading in the total light pattern. So this has been a significant improvement upon any of the previous designs, although obviously we could make it a little bit better still. But we also have to remember that I have the detector surface at one fixed location, and typically what we want to be able to do is to illuminate over a wide range of distances, which means we need to have a narrow angular spread. And in this particular case, what we see is, yes, we're getting a good energy distribution, but at the cost of having a somewhat wider spread of energy, although in this particular case, most of the energy is within, say, a 10-degree bundle, based on the information we see down here. So again, there are always going to be trade-offs in any illumination design, and sometimes to get a better irradiance pattern, it is at the expense of the angular spread of the light. This next example represents a departure in some ways from what we've looked at before. In this case, we've used a spline curve, if you will, or a free-formed optic, and what we see is the light, again, a lot of it is relatively collimated, but the shape of this reflector departs significantly enough from the parabola that, yes, we see some collimated light coming out, but we also notice that quite a bit of the light is diverging significantly, and even some light that reflects that is converging in this design. This simply is a way of showing you that you can readily create free-form type optical components within Apex. Now let's take a look at the results. In terms of irradiance distribution, in this case, almost all of the energy is concentrated near the center of our illumination pattern. So this would give us a type of reflector that's very good if we're trying to get a very neatly focused beam of energy. But of course, we also need to worry about what the angular spread is. And you'll notice in this case, not only do we have a nice narrow energy pattern, we also have a very narrow divergence. So we would see that energy distribution, that narrow energy distribution, over a relatively long distance. So although this doesn't behave in the same way the other reflectors do, it has a great deal of benefit for certain types of illumination applications. And finally, just to add a little bit of fun to this problem, what I've created is a surface based upon our parabolic curve, and the basic section is still parabolic, but what I did was created two separate polygonal edges, one towards the center with one number of facets, and one towards the edge with a different number of facets, and then combine them all together in this, I will admit, somewhat unique shape. But again, what this allows you to see is the wide variety of surface shapes you can create and combine within Apex to try to get the necessary illumination distribution for your particular application. And let's take a look at the results very quickly. And you'll notice that we have, again, area towards the center with very little light, but very nice spreading beyond that. A little bit of effect due to the polygonal edges. But what you can see from this design is you'll get an idea of some of the ways you can perturb the shape of your base parabola to get a wide range of energy distributions. And again, we'll end up by looking at our angular spread. And in this case, we do have a reasonably wide set of angles, so we're not truly collimating our light. In this case, in the range of about plus or minus 12 to 13 degrees. But again, for some floodlight type applications, that's exactly what you want. So what we've looked at are several different examples of how to start with a base parabolic reflector and how to modify that shape to try to get what is best for your application.